Okay, so for all the basic problems that I just mentioned in the previous part, let's see what can be done without thinking too much. Given a graph and vertices u and v, can u reach v? Well, you can just do explore from EU and see if u reach v, right? Namely, is v in reachable of u? And that, of course, also solves the question of computing the reachable set from u. So that takes O of n plus m time, and you can do graph explore, either DFS, BFS, doesn't matter. Okay, now this is the stranger thing we want to compute for u, all the vertices v that from v can reach u, right? This is the reverse reachability, and as the naive thing, of course, is to do, it takes quadratic time because for every vertex you do DFS, but you can do something much simpler. You just reverse the graph. What does it mean to reverse the graph? If you have an edge uv in a graph, create a new graph where all the edges goes in the other direction. Right? So clearly you can do this in n plus m time. In fact, it's not so clear. Think about how to do it. Make sure that you see the low-level detail needed to do it, but it's really not very difficult. Okay, so you compute the reverse graph in, as we said, of n plus m time. And now in this reverse graph, all the vertices that originally can reach v, right? Sorry, all the vertices that from them we can reach u, right? U is in the reachable of v. Now in this graph are just going to be in the reachable of u. So we just compute reachable of u in the reverse graph. And the correctness is intuitively clear. You can verify that you can prove it. Reversing the graph takes linear time, as I said. And as such, overall it takes O of n time. Okay. Now, if by some chance you have a representation where you have the incoming edge for every vertex, then you don't even need to reverse the graph. And then it's, even easier, but doesn't really matter for our purposes. Okay, computing the strong connected component of a graph is now very easy, right? Because we just compute, all the vertices that can reach u. Sorry, let me try again. All the vertices that are reachable from u and all the vertices reachable from u in the reverse graph. Both operations we can do in linear time. And now we just have two sets of number taken from 1 to n, right? So we can think about the set as just being a binary array with n bits on or off if they're in the set. And you just have to compute the bitwise as of those sets. And we can do this in linear time. So computing the strong connected component of u is as such easy and takes linear time. Okay, and how to do it in linear time I just described, right? Just use this bit vector array representation. Here is an example. So what is this? Right, so this is the original graph. This is the reverse graph. We just reverse the edges. This red set is all the vertices reachable from the original vertex. Right? Those are all the vertices that can reach, that are reachable from B in the reverse graph. And now we just take the intersection of the two sets. We get this purple set, which is indeed the strong connected component of the vertex B, which is what we wanted. Okay, if a graph is strongly connected, well, just pick a vertex in the graph, compute its strong connected component. We now know how to do it in linear time. We just verify it contains all the vertices in the graph. So this is O of n plus m. Finding all strong connected component in the graph is now going to be more painful. So the naive algorithm is just, as long as the graph is not empty, find the vertex, compute its strong connected components, remove it and repeat. By remove it, I mean remove all the vertices in this strong connected component and all the edges adjacent to this graph. So every inner iteration is going to take n plus m time, if you think about it. So overall, this is going to be n times n plus m. And it's not completely obvious how you can do better. It turns out you can do better, but it's going to be, as I said earlier, much harder. This is it.